Good evening. Hello. Good evening, everyone. Thank you for coming, and welcome to this latest edition of our lecture and stargazing series here at Caltech's Astronomy Department. My name is Anna Ho, and I'm a graduate student here in the department studying the catastrophic explosions that accompany the deaths of massive stars. I'll be on the panel later, so happy to talk more about that. But for now, let me start by telling you about the schedule for tonight. First, for about 30 minutes, we're going to have a lecture here in this auditorium. And then after that, we're going to break and continue the program in two different places. In here, we're going to have a Q&A with a number of panelists, including myself, Dylan, Maria over there, and Ron. And we are experts on topics ranging from gamma ray bursts to star formation to supermassive black holes, which are relevant to the talk tonight. So stick around for that and ask questions to your heart's content. Or if you'd like, we will have stargazing out in the fields that way. So you exit the building where you came in, take a right, another right, walk outside those windows there, and you'll find the fields back there. If you get lost, there are volunteers who have these badges. Actually, Maria, Ron, would you mind waving your badges? You can ask any of them for help with directions, and they can help you get where you need to go. A reminder about the fields, I have to tell you that there are various things you cannot bring there or do there. You can't bring food, you cannot drink, you cannot smoke, you cannot bring pets, and you cannot wear high heels. And that is because there is astroturf there, and if we do any of those things, we may not be allowed to use them again in the future. So please help us with that. I've been in touch with our lecture captain for tonight, and he's told me that the weather looks great. They have telescopes pointing at the moon, at Orion, and at either the double cluster or the Pleiades tonight. All right, so before I introduce our speaker, let me just tell you a bit about the swag that we have outside. We have these pictures you can take home. This is an X-ray image of Sagittarius A, which is the supermassive black hole at the center of our Milky Way galaxy. And Leo's told me that he's going to talk about this a bit during his lecture tonight. Finally, we also have a schedule of upcoming events for this term. So as part of the Stargazing and Lecture series, the next one is by Marta Bryan, a good friend of mine, on April 20th, about how gas giant planets shape planetary systems. So you should definitely come back for that. And then on the other side, we have a schedule for our Astro on Tap series, which takes place at Der Wolfskopf, this bar in Old Town. We give short presentations in the bar. You can have a drink and listen to sort of more informal talks about astronomy. So without further ado, it is my great pleasure to introduce Leo Stein, a friend and colleague in the department. Leo is a postdoc who does research on black holes. He also, in his free time, tells me that he likes to do crossword puzzles. So with that, I'll hand it over to Leo.
Thanks, Anna. Can everybody hear me okay? Is the mic working? Okay. Are you excited to learn about black holes? Good, great. Okay, so there's a huge amount of stuff to learn about black holes, and this is only supposed to be a half-hour talk, and Anna is going to pull me off stage if I end up going too late. So I'm just going to tell you a little bit about black holes. You could study this topic for years, and you would still not know everything there is to know about black holes. So I'm just going to tell you a little bit, and maybe it'll whet your appetite, and you'll end up studying black holes too. Okay, so what is a black hole? A black hole is the most compact thing that you can have in the universe at a given mass. So if you take a certain mass of a thing, say something like the sun has a certain amount of mass. It also has a certain size. If you squeeze it down, keep squeezing it until it gets smaller and smaller and smaller. Once it gets to a certain size called the Schwarzschild radius, you won't be able to make it any smaller. There is nothing in the universe that has the mass of the sun that is smaller than the Schwarzschild radius of the sun. There are things that are smaller than the Schwarzschild radius of the sun, but they all have less mass than the mass of the sun. So there's no way to compress anything more than its Schwarzschild radius. If you get something down to its Schwarzschild radius, it will become a black hole. Okay, so how does this happen in the real universe? One common way that this happens in the universe is when really old or really massive stars get to the end of their lives, they end up dying. Some stars live for a really long time. Really massive stars end up dying, and sometimes they have a catastrophic end of their life called a core collapse supernova, and sometimes that leaves behind a black hole. So here's an example. One of the first, we call these stellar mass black holes that was known, called Cygnus X1. That was discovered in 1964 thanks to X-ray observations. That's what the X means. This means that it's found in the constellation Cygnus, and it was the first one that was found. So this thing is about 6,000 light years away. It's about 15 times as massive as the sun, and the way that we know its mass is because it's orbiting a companion that is a blue giant star that is blowing off a lot of gas, and that gas is getting sucked into this black hole, and that black hole is spitting it out, and we're seeing the radiation that's coming out of that. And we can see these one star, one black hole, orbiting each other every 5.5 days, and the distance between these two objects is just 1/5 of the distance between the Earth and the Sun. So that's a pretty extreme object. So objects like these that are between 10 and 30 times the mass of the Sun, we call them stellar mass black holes. Now, when this thing was first discovered, astronomers weren't positive that it was a black hole. The idea of black holes was still kind of new. So Kip Thorne, who's a Nobel Prize winner in this building, and Stephen Hawking, who sadly passed away last week, made a bet back in 1974 about the nature of this astronomical object called Cygnus X1. And the bet was about whether or not this thing really is a black hole. So you can see here that whereas Kip Thorne likes to live dangerously without an insurance policy, they made a bet about whether or not this object really is the thing that these two folks dedicated their lives to studying. And you can see here that in 1990, Stephen Hawking conceded the bet because there was so much evidence that, yes, this thing really is a black hole. Okay, so that's one type of black hole that we observe in the sky, stellar mass black holes. We also have supermassive black holes. So as far as we can tell, most galaxies, like the Milky Way and bigger galaxies, have supermassive black holes in their centers. This one is the heavyweight champ. This fuzzy-looking blob here is actually an enormous galaxy called NGC 4889. And scientists measure how fast stars are moving around very close to its center. And using the measurement of the velocity, they've inferred that there's a giant black hole in the middle that is 21 billion times the mass of the sun. This is the record holder that we've found so far in the universe. So we have black holes between 10 times the mass of the sun, 21 billion times the mass of the sun. So here's a mystery. We don't exactly know how these supermassive black holes were formed. Now, we understand that when galaxies crash into each other, which happens throughout their lifetimes, this happens very slowly, but every galaxy seems to experience about one major merger in its lifetime. If they have supermassive black holes, those black holes slowly sink to the center of the newly formed galaxy, and eventually those black holes find each other and merge, and so they can grow, and they can eat gas and stars from around their environment and get bigger and heavier. We understand how this process works if we start out simulations with black holes that have thousands of solar masses. But there's this gap. We've observed black holes that are stellar mass between 10 and 30 times the mass of the sun, and we don't understand how to go from 30 times the mass of the sun up to these seed black holes that are needed, starting from a few thousand times the mass of the sun, up to get these millions to billions of solar mass black holes. So the stuff in the middle we would call an intermediate mass black hole. We've never observed anything in that gap between 100 and a few thousand times the mass of the sun, but we think they might be out there. We've never observed them, and we don't understand how these supermassive black holes were seeded. So this is a big mystery, and people are working on this. Okay. Here are some more interesting things that supermassive black holes do. So supermassive black holes are extremely powerful objects. You can see their effects from across the universe. These are some of the most distant things that we can see. When we see them very far away, usually we call them active galactic nuclei, because the reason that we're seeing them is because they're eating a lot of gas, and that makes it all very bright and hot, and they're spewing out lots of radiation, and that's the radiation that we're seeing. So one of the really cool things that they can do is that they can launch what we call jets. So this is a composite image of a galaxy that has an active galactic nucleus called, it's in the Centaurus constellation, and this is Centaurus A. And we think that the black hole that's in the middle here is 55 million times the mass of the sun. And if you take how far away it is and you do some geometry, you find out that this thing is blowing bubbles into the gas that's between the galaxies. It's blowing bubbles that are at least 200,000 light years long. That's huge. So there's a nice zoom-in image here that you can find. So this thing was taken with optical and radio and X-ray. And this very innermost part was taken with radio, with a technique called very long baseline interferometry, VLBI. So using radio dishes that are on the opposite sides of the Earth and combining these radio dishes into one huge telescope, scientists can make a telescope that has even finer resolution than any of the individual telescopes by themselves. So that allows you to see really, really fine details down into the middle of this galaxy. So we think that there's a supermassive black hole here, and it's launching these jets that are going, as far as we can tell, about 99.9% the speed of light. And they're shooting out there for around 200,000 light years long. So these are extremely powerful objects. Okay. All right, here's another mystery. We don't understand how these jets get launched. We see these jets getting launched. We know that there's some magnetic field stuff going on, but people can't do these simulations yet. They can't make simulations for black holes launching gas to 99.9% the speed of light. This is a big open question in the field of active galactic nuclei. We don't know how to launch jets. Okay, so we're at Caltech, so I have to give you a quiz. All right. So from what you've heard so far, do you think the Milky Way has a supermassive black hole? Okay, decide for yourself. Talk to your neighbor. Find your neighbor. Yeah? Okay. Now, raise your hand if you think that the Milky Way has a supermassive black hole. Okay. Raise your hand if you think the Milky Way does not have a supermassive black hole. Okay. Most of you are right. The answer is yes. There is a supermassive black hole in the middle of the Milky Way galaxy. And we call this thing Sagittarius A star, and it's actually what you might have been able to pick up outside if there were some left. This one is from X-ray observations. Now I'm going to show you a movie from the UCLA group that was done using infrared observations over the past 20 years. Hopefully it'll work. There we go. Okay, so you can see the date up in the top right. So this is starting back in 1996. And this is the location where we think there's a black hole. And each of these blobs is actually from infrared observations of a whole bunch of ordinary stars that are going around this spot. But there's no infrared radiation coming out of there. There is a little bit of radio. So if you look at these orbits and you do some calculations and you ask, how heavy must the thing in the middle that we don't see be, you'll find out that it is around 4 million times the mass of the sun. Okay, let's close that. Okay, so this is around 26,000 light years away, and we think it's around 4 million times the mass of the sun. All right, so we just saw those stars going around a black hole. We know in our own solar system, the moon is going around the Earth is going around the sun. What is the sun going around? Is the sun going around the black hole that's in the middle of the Milky Way galaxy? This is a myth that I've seen online, so I just wanted to bust this one. No, the sun is not going around the supermassive black hole that's in the middle of the Milky Way galaxy. In fact, that black hole, it's huge. It's 4 million times the mass of the sun. But if you take the mass of the entire Milky Way, it's around, what is that? Million, billion, trillion. It's actually close to 500 billion times the mass of the sun. So there's way more mass in just ordinary stars and dark matter that I'm not going to talk about in the Milky Way. That's what we're going around. So all of the stars are going around each other, not around this one. Of course, these dozens of stars in the middle are going around the supermassive black hole. That's because they're really close to it. But the rest of the stuff is just going around the combined gravity of all of these stars. Okay. Okay. Time for another pop quiz. When do you think that black holes were first proposed? A, 1783, B, 1916, or C, 1964? Okay, take a second, decide for yourself. Okay, talk to your neighbor. Okay. All right, raise your hand if you think it was 1783. Okay, raise your hand if you think it was 1916. Okay, raise your hand if it was 1964. Okay, it looks like the 1916s had it, but the real answer is 1783. Okay, yes, this should surprise you because this is more than 100 years before Einstein's theory of special relativity, which is one of the key ingredients that you need to understand black holes. So the first prediction of black holes was made by this fellow John Mitchell, who was a cleric in England in 1783, who also did some science on the side. And Pierre-Simon Laplace in 1796 basically came up with the same prediction, but they didn't know about each other's work. So this is one half of the equations in this talk. So this calculation was kind of wrong because they didn't know that the speed of light was constant. They just knew that this was the fastest speed that anybody had ever measured. But the speed of light was known that time. And Newton's constant big G wasn't known by itself, but the combination of G times the mass of the sun was known. Okay, so for every planet or star or ordinary body, there's this thing called the escape velocity. When you take, this is, sorry, my bad art. When you take a cannon and you shoot a cannonball, depending on how fast you get that cannonball going, it'll go a certain distance. If you shoot it faster, it'll go farther. If you shoot it even faster, it'll go even farther. If you shoot it fast enough, you can actually get a cannonball to go into orbit around the Earth. Now, the escape velocity is the speed that you need in order to get a cannonball, if you just shoot it out of a cannon, to just leave the Earth and not come back. That's the escape velocity. So you can get it by combining a bunch of numbers. You can get it by combining the speed of light and the mass, you can get it by combining Newton's constant and the mass and the size of the body. Now, what Michel and Laplace did was they turned that around and said, if I had a certain body of a certain mass, by how much would I need to squeeze it down so that the escape velocity at the surface was the speed of light? And that thing is now called the Schwarzschild radius. Now, they got kind of the right answer, but for the wrong reason, because they didn't know about special relativity, they didn't know about Einstein's theory of general relativity. But this thing of just combining the numbers to get something with the right dimensions is called dimensional analysis, and we do this in physics all the time, and it's super important. So essentially, it worked because dimensional analysis worked. Okay. The problem is, light is not cannonballs. This is not what a black hole is. So now I'm going to tell you what a black hole really is. Okay, so we're going to do a little thought experiment by analogy. So we're going to imagine that we're going to go to the river, and we're going to take a stone, and we're just going to drop it in, and we're going to look from above what happens. So what's going to happen is there are going to be some ripples that go out. As you wait longer, the ripples will go out. So if this was before the digital age, then we would have a bunch of pieces of film, and we could either make them into a flip book or stack them up. So let's stack them up into like a flip book. So this is called a space-time diagram. So time is going up, and space is going sideways. And these are the frames of our movie. So this is when the stone first hit the water, and there's the first ripple going out, and then it went farther out, and there's the farther out. So what you'll see is that there's this cone shape when we first drop the stone in, and here is the outermost boundary of the ripples. So the shape of this cone just comes from how fast are the ripples allowed to move. Okay, so now let's say that instead of the water just sitting there, what if this is really a river and the water is moving? So if you drop the stone in, the ripples are going to go along with the water. So if we make our new movie and we stack it up, then the cone is going to tip over. And if it's going even faster, then it'll tip over even farther. And the faster it's going, the farther this cone tips over. So you can see that if the speed of the river is faster than the speed of the ripples propagating on top of the river, then the cone will tip over so far that it's not even vertical here. So the direction that's going forward in time is no longer inside the cone. Okay? All right, so this was just one spot in the river. Now let's imagine the entire river. So here's the river. Every spot has its own cone of where the ripples are allowed to go. the ripples can only exist inside the cone if we drop rocks here, 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 here. Now, let's imagine that there's a sinkhole in the middle of the river. So the water wants to flow towards the center of the sinkhole down into the middle. So if the closer to the sinkhole you get, the faster the water is flowing, that means that the cones are going to tip farther inward. So if you drop a stone in here, then the ripples are going to get sucked down into the middle. So the information about dropping that stone in can't go back upstream. The same thing is true in space-time. Now in a river, of course, if you have a motorboat, you can go faster than the speed of the ripples. That's why you make a wake. But in space-time, that's not possible. The speed limit in space-time is the speed of light. So if you know how fast light is moving, you know how fast everything is allowed to move. Nothing can go faster than light. So we can make the same kind of diagram for a collapsing star in space-time. Now this is some complicated thing, but again, time is going up, and at every point in space-time, we can ask, where is light allowed to go? So if we were sitting here and we had a flash bulb that was going off, then light would be expanding outward and it would make a little cone. Now, if this matter is if this is a star that's collapsing inward because there was a supernova and it can't support itself, it's possible in this very complicated theory called general relativity for this matter to hold itself together with so much gravity that eventually you don't even need the matter to hold it together. And all you have is gravity that's holding itself together. And what that means is that there's this boundary that we call the event horizon where all of the light cones are tipping inwards. So if you set off a flash bulb here, all of the light goes inside of this cone. It all has to move inward towards the middle of this region here. None of the light is allowed to move outward. So this is how people who study general relativity think about a black hole. So notice I didn't say anything about singularities. I didn't say anything about anything breaking down. I'm talking about the event horizon. So really what we think about defining a black hole is the event horizon. It has a size, and that size is given by the event horizon. There could be some crazy stuff going on inside. There could be a singularity. The math could be breaking down, or it could be rainbows, or it could be pink unicorns. We don't know. But that information will never make it outside because all of this stuff has to go slower than the speed of light, and the light cones are pointing in, so this information can only go this way. It can't go out that way. That's a black hole. That's what we mean. Okay, time for another pop quiz. All right, what would happen if we would replace the sun with a black hole that has the same mass as the sun? A, we get sucked in, B, nothing, or C, we get flung out. All right, decide for yourselves. Okay, talk to each other. Okay, who thinks that we get sucked in? Okay, who thinks that nothing happens? Okay, who thinks that we get flung out? All right, the B's seem to have it, and you're correct. Nothing would happen. Okay, so this is the second myth that I wanted to bust, that black holes are cosmic vacuum cleaners. They're not vacuum cleaners. As long as you're not too close, you're not going to get sucked in. So that's a myth that I busted. All right, so let me show you okay, so the point is, we saw these stars orbiting around the supermassive black hole in the middle of our galaxy, Sagittarius A star. So we know that it's possible for stuff to just orbit around a black hole with no problem. These things are not getting sucked in. So let me show you some cheesy Mathematica simulations that I made to show you this. Okay, so this is a regular star on the left. Can you see this? Yeah, regular star on the left and a black hole of the same mass on the right. And of course, I programmed this, so it's going to do what I want it to do. But the point is, do you see any difference between the left and the right? In general relativity, as long as these things in the middle have the same mass, if they're both spheres, then you're going to get the same motion around them. Okay. So the other thing that I wanted to tell you that I had on this previous slide is that when you're far away from a black hole, the speed that you orbit is almost the same as if you were in Newtonian gravity. So here's another cheesy animation. So here we've got orbits that are 50 Schwarzschild radii away from these black holes. All right, do you see the difference between these two? It's a very subtle difference. The one on the right is in Einstein's theory, general relativity. The one on the left is in Newton's theory of gravity. The one on the right is orbiting just a tiny bit faster. If we make this closer, so let's make it orbit at 6 Schwarzschild radii. Now there's a much bigger difference. So when you're really close to a black hole, there are big differences, but far away, the differences are really tiny. Okay? All right, back to the slides. All right, so even though the differences are really tiny, the differences are really tiny when you're asking how long it takes to orbit around it, one thing that is very noticeable around a black hole is how light moves. Because even if we're far away from a black hole, we can see light that's going close to a black hole. So this is called deflection of light. So if there's a black hole sitting in the middle here, and we shoot in light rays at different distances away from the black hole, then these light rays will get bent by different amounts. Now, in Einstein's theory of general relativity, light wants to move on the straightest possible paths in space-time. The problem is that all of these light cones tipping in is a manifestation of the fact that space-time itself is curved. So when light rays want to move on straight lines in curved space-time, to us it looks like the light is getting deflected. So if you shoot a light ray far away from a black hole, it doesn't get deflected very much, but the closer you shoot a light ray, the more it gets deflected. And there's some critical distance very close to the black hole that's called the photon radius, where if you shoot a photon at that radius, then it can just go in circles at that spot. Okay, so understanding this was crucial for Einstein's theory to be accepted in 1919. So this was one of the major tests of the theory of general relativity. This was right after World War I. People wanted to see whether or not this deflection thing was real. So Sir Arthur Eddington and collaborators set out to do a test in the solar system. How much is light deflected by massive bodies? Now, in the solar system, the most compact thing we have in terms of dividing the mass by its size is the sun. So we want to look at light that's going very close to the surface of the sun. The problem is the sun is really bright, so it's really hard to look at dim stars that are behind the sun and see their light close to the sun. So what they did is they waited for a total solar eclipse, and they knew where the eclipse was going to be, so they had to travel to this island, Principe, and they observed stars near the sun during the total solar eclipse. And is it dark enough in here? Well, if it's dark enough, you can see there are these little white dashes here that are pointing out the locations of stars. And those stars shifted by just a hair relative to where we would have seen them if the sun hadn't been there. So if we wait 6 months and we look in the same direction in the sky, now the sun is behind us, we can see where those stars would have been, and you can measure the difference that they shifted. So this is what made Einstein famous, the confirmation that, yes, light really is deflected by as much as Einstein's theory of general relativity said. So this led to this kind of funny New York Times headline that I like, although it's a little sexist. Men of science more or less agog over results of eclipse observations. Einstein theory triumphs. Stars not where they seemed or were calculated to be, but nobody need worry. Okay. All right, so let me show you another little demo about this photon sphere thing. So if you go to my website, you can just search for my name in Caltech and you'll probably find it, and click on Kerr spherical photon orbits. And there's this little toy that you can have that shows you, let me make it smaller. So here's a black hole. Black holes in general relativity are allowed to spin, and this blue arrow is showing the direction around which it's spinning. And when they spin, you can have photon orbits at different radii. So we can change the radius of the photon orbit. The closest photon orbit is just a circle, and the farthest photon orbit is also just a circle. And in between, there are all sorts of crazy orbits that go up and down. Let me make this shorter so you can see. This is the path that a light ray would take as it's going around a black hole. And there are some really cool places. So let me make this longer so you can see where it's been. There are special places where the light trajectory will overlap on itself and make these things that are called Lissajous figures that look like flowers. They're kind of pretty. Okay, so you can play with that if you want to. Uh-oh. No. Okay. All right, let's continue. So Instead of that cheesy little web thing, there are also people who do numerical simulations of black holes, and they can make movies like this. So if you were orbiting a black hole and you could see the entire plane of the Milky Way galaxy, this is what it would look like if you were always looking towards the black hole, going around, so you get to see the Milky Way in different directions around you. There's some really crazy lensing that goes on. Okay. So that's pretty cool. I'm going to skip this and also show you this one. So this is what it would look like if you were near two black holes that were going around each other. And if you look really carefully, you can see that there's a kind of black eyebrow going around each of the black holes. That is an image of this black hole that is being lensed by that black hole. There's lots of crazy trajectories that go around. These things are getting closer together because gravitational radiation is dissipating energy from the system, and they just merged into one black hole. This is on YouTube too. Oh, and all of these calculations are taxpayer supported, so thank you for paying your taxes. Okay, running out of time. All right, another pop quiz. Would you rather fall into a supermassive black hole or a stellar mass black hole? Okay, yes, you could also choose to not fall into a black hole at all. All right, there's no right or wrong answer to this one, because if you fall into a black hole, you're not coming back. And in fact, something really bad will happen. My clicker won't work. You will get turned into spaghetti. So this is something called spaghettification. This is a real word that scientists use. This is not a made-up word. We actually use this word. So spaghettification is what happens when there's a tidal force on you. So what is a tidal force? It's just a difference in how much force there is pulling on your feet versus on your head. So if you're falling feet first into a black hole, your feet are closer to the black hole, so there's more pull on your feet than on your head. And your sides are not just being pulled down, they're also being pulled towards the center. So that means that you're being squeezed in this direction and you're being stretched in this direction. So when you fall into a black hole, you get spaghettified, you get stretched out in this direction, you get ripped to shreds. Okay, so the one thing to remember is that the strength of the tide at the location of the event horizon is determined by the mass of the black hole. So smaller black holes have bigger tides, and bigger black holes have smaller tides. That might sound backwards, but this is what happens when you plug in the numbers. So if you want to be able to experience going through the event horizon and see what it looks like, then you should go through a big black hole, and it'll take you maybe a minute before you're ripped to shreds. But if you just want a quick and probably painless death, then you should jump into a smaller black hole. Okay, the final myth that I want to bust is that black holes are black. I've been telling you they're black, and everybody tells you they're black because light can't escape, so you won't be able to see anything coming out of them. And that's true, except when you combine it with quantum mechanics. So this was Stephen Hawking's most important contribution to science. So Stephen Hawking was the first person to ask, what happens when I add quantum field theory to black holes? And he did this kind of complicated calculation, but it's a rigorous calculation that everybody trusts, and we agree that the result is true. And it says that there's a teeny tiny amount of radiation that comes out of black holes. This is electromagnetic radiation and gravitational radiation. And this radiation carries energy. So because E equals mc squared, if energy is going away from a black hole, it must be coming from the mass of the black hole. So as energy is very, very slowly leaving a black hole, the mass of the black hole is shrinking and shrinking and shrinking. And eventually, the black hole will disappear. We don't really understand how that process is supposed to happen, and we're never going to see it for astrophysical black holes, because when you plug in the numbers, the amount of radiation from astrophysical black holes is just way too small to ever observe this. But we trust the calculations. The problem is, you can make a black hole out of different things. You can make a black hole out of a star. You can make a black hole out of encyclopedias. You can make a black hole out of unicorns. And that's information. So there are different ways to form a black hole. But if a black hole radiates away, and all you have left over is the radiation, and this radiation doesn't have any information about what fell in, there's a problem for quantum mechanics, because this means information has been destroyed. And if you turn the statement that information has been destroyed into numbers, what that really means is that probabilities stop adding up to 100%. In quantum mechanics, everything is probabilistic, but there are still rules. And the rules say that if you take all of the possible outcomes and you ask, what are all the possible things that could happen in the world, and you add up the probabilities, there's always going to be 100% probability that something will happen. If information is destroyed, that means that the rules get broken, and the probabilities stop adding up to 100%. They could add up to less than 100%. They could add up to more than 100%. And nobody knows what that means. So it seems like black holes are big trouble for quantum mechanics. Now, this was another famous bet between Stephen Hawking and Kip Thorne and John Preskill, who is another professor here. And the bet was about whether or not black holes really do destroy information. So this is such a crucial concept to quantum mechanics that we just can't let black holes destroy information. So there are different sides to the bet, but Stephen Hawking was betting on black holes not destroying information, and in the end, he conceded this bet too. He got turned around by John Preskill and other people in the community saying, no, we still have to have probabilities adding up to 100%. So we don't know how to resolve this problem, but Stephen Hawking, who was the first person to realize this problem, has gone back on it and said, there has to be some solution. I don't know what it is, but there is a solution. So this is the biggest mystery, in my opinion, in physics today, in fundamental physics. We don't know whether or not black holes destroy information. We hope they don't. But if they don't, we don't know how that happens. We don't know how to fix the calculations. We don't have a theory of how black holes and quantum mechanics together can make sense. We don't have predictions that work. So people have been working on this problem for 40 years, and they're probably going to be working on it for another 40 years before we have a fully satisfactory answer. So those are most of the things I wanted to tell you. There are way more things than I could possibly tell you in 30 minutes, but maybe you'll remember some of them. Black holes are some of the most powerful things in the universe. They are not vacuum cleaners. As long as you stay far enough away, they're not going to suck you in. If you get too close, they will spaghettify you. They're not really black. They're kind of a very, very dim gray. There are a lot of mysteries we still don't understand about black holes. We don't know how supermassive black holes are born and grow. We don't know how they launch jets. And we don't know whether or not they destroy information or not. But there's a lot of people who are interested in black holes. There are a lot of young people here. So maybe some of them in the future will figure out these puzzles and will know the answers. Thanks. We can take a few questions. Yeah? How can you measure the event horizon of a black hole? Yeah, that's a really good question. So the answer is kind of technical. The problem is the definition that we like in this theory of general relativity is that the event horizon is really the boundary between things that can escape and things that can't escape. And to answer the question of where in space-time can you escape away or are you doomed to the inside, really means that you need to know the entire future history of space-time. So this is not a question that you can answer locally. You can't look at a little patch of space-time and answer, is there an event horizon here? The definition doesn't let you. There are other technical things called apparent horizons that you can find out, and that's a question about whether or not, if you set off a flash bulb, does the light expand or not in a small region? And for black holes that are kind of not changing with time, the apparent horizon and the event horizon are the same thing. This is a kind of technical thing. Yeah? Are black holes able to suck in anything? I want to say yes. But if you have two black holes that are merging together, I don't know if it makes sense to say that the smaller one sucked in the bigger one or the bigger one sucked in the smaller one. Really, the two black holes just kind of merged into one bigger black hole. But that's not really a sucking in thing. So, yeah, in the back? Yeah. Okay, I think the first part was, can black holes die and explode like stars do? Was there a second half? Yeah, so if we believe this calculation, which as far as I know, everybody believes this calculation from Stephen Hawking, that black holes do radiate in this process called Hawking radiation, then as they get smaller and smaller and smaller, they radiate faster and faster and faster. And in the end, there should probably be a burst of radiation that's kind of an explosion. So that would be ultimately the death of the black hole, because there would be no black hole left over. But this process takes an incredibly long time for astrophysically sized black holes. So we're probably never going to observe it. I don't think we'll ever observe it. Yeah? How long can black holes live? Okay, so I need to do the calculation. But the biggest black holes in the universe will live the longest because of the laws of Hawking radiation. So maybe I'll do the calculation while we set up for the question and answer panel, and then I'll tell you the answer to that.
All right, thank you for your patience. We're going to get started with the panel Q&A now. So there are four of us who work in various different areas of astronomy, as you can see here. This is relatively free form, totally informal, so please feel free to ask us whatever questions you have. Maybe to get things started, we can just go down the row and introduce ourselves, say sort of who we are, and just in brief what we work on. So I'll start. I'm Anna. I am a graduate student here at Caltech, and I study the deaths of stars and the corpses they leave behind. So those are supernovae, gamma ray bursts, pulsars. To do that, we use a technique which you can think of as a kind of celestial cinematography. It's like making a movie of the sky to search for explosions that come and go.
Hi, I'm Dylan. I'm also a grad student here at Caltech, and I'm a radio astronomer primarily, and I use the Very Large Array, which is a set of 27 radio dishes in New Mexico that all combine together to form one giant telescope. And I study various things from the births of stars, these star-forming regions in nearby galaxies, to the deaths of stars, these supernovae and gamma ray bursts that you might see in slightly farther away galaxies.
Hi, I'm Maria. I'm a postdoc here in the department. And as you can see, I work on supermassive black holes. I usually study supermassive black holes when they are in pairs from galaxy mergers and when they emit gravitational waves.
Hello, my name is Ron. I'm also a graduate student here in physics at Caltech. And so I work with LIGO, so I work on gravitational waves, do some stuff with general relativity and how we test it.
All right, so let's just get started. Any questions? Yes.
When you look at a black hole, why do they look planar? Like, if it's a hole in three-dimensional space, why are the jets going off only in two directions?
So the question was, when you look at a black hole in images and it has jets coming out of one pole and the other pole, why is it that normally it seems like we're looking at them edge on? So I would think, and others should chime in, and Leo can chime in, that, there is no preferred direction to these things. So probably when people are choosing images to show you, they're choosing images that look the nicest. And the images that look the nicest might be with them coming out of those poles.
Right, but why is it in two directions? Why if you think of radiation coming off from a point, shouldn't it look like the sun? Shouldn't it be coming out in all directions?
So when we talk about a jet, it has a preferred direction. So material is flown away in a specific direction. So you're asking why. The truth is we don't totally understand the process, but there are two interesting things that are happening. The black hole is spinning, so maybe the material are flown away in the direction of the angular momentum, and we have the formation of magnetic fields. And again, we don't understand the process, but maybe the magnetic fields are preferentially created along this direction if the black hole is spinning in a specific way.
So black holes have an orientation by its spinning. That's what you said?
Yes.
Okay, thank you.
Question for the jet itself, when we mentioned that it was close to the speed of light, but how does it, do we know how it escapes, in a sense, the black hole, if we know that, it's not even the speed of light, it's like to get out, how it's not even possible? And as a follow-up, does the trajectory change once it gets out of the horizon? Does it kind of try to pull it back in?
Yeah, so the question is, black hole jets are traveling very close to the speed of light, but slightly slower than the speed of light. And how does it escape the black hole? Well, it doesn't actually come from within the event horizon itself. It gets launched from places that are outside of the event horizon. So nothing can escape from within the event horizon, but plenty of things can get launched from, a few times the Schwarzschild radius above the black hole, for example. And sorry, what was the second part of your question?
I just wondered if it gets affected, the trajectory gets affected by the black hole itself.
Okay. Does somebody else want to take this one? Or I suppose if it hits material on the outside, then you can get sort of deflected. I don't know about general relativistic effects very close to the black hole. But
Yeah, so if it's too close to the event horizon, it actually gets redshifted, because you can think of it as the strong the gravitational field is sort of pulling the wavelength of light apart in a way. You can think of it that way. So that's kind of very similar to why when you get closer to a black hole, you appear to be more redshifted to people who are far away from the black hole. And that's kind of also the same reason why is that when you fall onto a black hole, you sort of disappear. So what actually happens in that process is that you are frozen on the surface of that black hole, but yet since the black hole is the strongest thing that we know, what happens is that you get infinitely redshifted, so your entire image just starts to disappear. And when you get infinitely redshifted, you're essentially dark.
I don't know about this,
Okay, I'm supposed to speak into the microphone so that people will watch this later and know what we were talking about. So the question was about how whether or not there is actually information encoded in the radiation, and that's been a puzzle for a long time, and people hoped that indeed the information really is somehow encoded in the radiation in some maybe very complicated way. So it looks like it's totally random and statistical and thermal, but it secretly encodes stuff, information about what fell into the black hole. But there's, even if you and people have tried to, figure out whether or not that's possible. John Preskill worked on this. Sean Carroll has worked on this. A lot of people have worked on this. And it's possible that, the radiation that's coming out is actually what's called quantum entangled with other radiation. So while it looks like it's random, it's not actually random in a certain way. So if you could measure maybe all of the radiation and put it back together and reassemble it in a certain way, then you would actually have all of the information that fell into it. Unfortunately, I think that's not, the current understanding is that it can't just be entangled with other radiation. There's not enough entanglement possible, or in fact, if you compute how much entanglement is possible, then you find out that there's way more entropy in the radiation than there was that went into making the black hole in the first place. So there's still an information problem when you try to, reconstruct the information that went in out of the Hawking radiation. There's still puzzles. What is the status of the black hole information paradox? I would say still very open. I don't know more than that.
In the evolution of the universe from the Big Bang to now, was there ever a time when black holes did not exist? That is to say, is there certain prerequisites for the creation of a black hole? And then second is, why didn't the early universe collapse back into a black hole? It seems like there would be a lot of mass and a lot of opportunity there.
Does anybody want to, or I can answer? Yeah. Okay, so this is a two-part question again. The first one was, sorry, could you repeat? Yeah. Oh yeah, right. So was there ever a time when black holes didn't exist? Yes, that was the first one. And the second one. Yeah. Mm-hmm. Yeah, and the second one was in the very early universe, things are very dense, and so why didn't it collapse back into a black hole? In the entire universe, why didn't it just turn into a black hole? So for the first question, yes, there was a time in the very early universe where we think that black holes didn't exist because there are only certain channels that we know of to form black holes at all. And Leo touched on this during his talk. The main mechanism that we know of is these core collapse supernovae. So in order to get a core collapse supernova, you have to form a massive star first. That star has to evolve, and it has to live for like 1 million years. And then it has to blow up, and the core has to collapse into a black hole. Right? And that takes some time. Right? So in the first, there's some time before you can form stars at all, and then there's some time for those stars to be alive. And then after that is when you get your first black holes. There are some theories that in the very early universe, you get very hot giant clouds of gas that directly collapse into black holes. But again, you have to cool enough to be able to collapse, and it takes some time to collapse as well. So yes, there is a time when black holes didn't exist. And the second question was, in the very early universe, why didn't it just entirely collapse into one giant black hole? I think, to the best of my knowledge, the forces that were expanding the universe, inflation in particular, although is the most popular theory right now, says that the universe expanded in some ridiculously rapid fashion in the first, 10 to the minus 40 seconds or something of its lifetime, growing by a factor, some ridiculous exponent as well, like 10 to the 50, I don't know. And, it just expanded way too fast to collapse. Mm-hmm.
And then, so then there exists some sort of force that doesn't allow black holes to collapse or whatever. Does that mean, can there exist a force that would allow a black hole supernova to,
Sorry, do you understand?
Sorry, so your question is, that in the beginning of the universe, the conditions were not right to form black holes. So, well, so there was a force that was, yes, there was a force that was causing the universe to expand so rapidly that it was much stronger than the force of gravity that would cause things to collapse again.
So therefore, can there be some sort of force that would exist, let's say within a black hole, that would allow it to explode, like into a supernova type situation, if I'm a star such that it would?
Oh, I see. So the question is then, since the universe was able to expand and not collapse into a black hole, could a black hole itself actually expand and explode? So I believe the answer is no, but I'm going to pass this on to someone who knows more than I do.
Yeah. So by the definition of what is an event horizon, since the event horizon is like the boundary between what can escape too far, arbitrarily far away, versus being trapped, if there was something like that, then that would mean that it wasn't a black hole in the first place. It might have looked like a black hole and acted like a black hole, but it wasn't really a black hole because in the end it could have, expanded. So that would mean, but that's just a definition thing, that it doesn't satisfy the definition of having an event horizon. But I think to actually, to have some sort of expansion that was rapid enough to, undo the collapse, would require some kind of exotic material that we're not familiar with. And in fact, that kind of exotic familiar must have been present to drive inflation as well. So maybe there is some stuff in the universe that has these weird properties that we don't understand, which, if you want to get technical and look it up later, it means that it violates certain energy conditions, usually the null energy condition. But this is some technical thing that what are the conditions necessary to get this expansion to happen fast enough? But we don't really understand the material.
What is the relationship between dark matter and black holes? More specifically, can dark matter help form black holes by acting as sort of like a sinkhole for matter to sort of coalesce on?
Well, I guess, so the question was, what is the relationship, if any, between dark matter and black holes? I think the short answer is that we don't really know, in the sense dark matter is matter that we know exists because we see it exert some gravitational force, but we don't actually know what it is. I think that one hypothesis is that it could be some black holes, but yeah, I guess only a very small fraction of it could even be black holes, but I guess some of it could be, but we don't know. That's all I know.
Yeah, and I guess the second part of that question was, could black holes grow by creating dark matter? Right.
Dark matter helps form black holes because, it's sort of like the cosmic nodes that sort of matter coalesces on.
Uh-huh.
So does it act like a sinkhole and allow matter to sort of accrete?
I see. Yeah, so so the question is, does dark matter help attract matter and help the formation of black holes? And so yes, dark matter does pull in stuff, but typically this sort of process happens on the scale of galaxies, not on the scale of black holes themselves. Dark matter is generally very diffuse, and the actual density of dark matter in any black hole-sized area is very, very low. But when you add it up together on the scale of a galaxy, then it becomes important. Mm-hmm.
So with 1,000 solar mass, so the frequency in which we're sensitive to LIGO ranges from 10 hertz to 4,000 hertz. So I would say 1,000 mass black hole would be like cutting on the kind of pushing on it, like on the noise curve below 10 hertz, because the more massive the black hole is, the lower the frequency is of the gravitational radiation. So I would say like 1,000 solar mass black hole might go below the LIGO noise curve. I don't know if you guys have any knowledge about that. Leo? Draw a picture. Anyways, yeah, I'll draw the picture. Okay, so over here on the x-axis, you have what we call the amplitude of the gravitational wave, call it square root s. And here we have the frequency of the gravitational wave, and this can also represent what your noise curve is. So you have 10 hertz right here of a gravitational wave. So for binary systems, like you have two black holes that orbit each other, and then they will have an orbital frequency. So the frequency of the gravitational wave would be twice this orbital frequency. And here in LIGO, we have a noise curve at 10 hertz. And this is set by what we call Newtonian noise due to fluctuations in gravity here on Earth. Not due to gravitational waves, but it's just inherent noise like ocean tides and things like that affect the stability of the mirrors for LIGO. So if you want to probe this lower frequency range where like 1,000 solar mass black holes would exist, you would have to build them in space. So over here, so for example, I should have drawn this all the way out. So over here, you would have like a LISA band over here, which would be in what we call the millihertz range. And those can go as high as like 1 million solar mass black holes in binaries. So in here is like about 1,000 hertz, I would say. And then as you get above here, this lower part is governed by thermal noise on the mirrors that we use. And then up here is another type of noise, what we call quantum noise for the LIGO detectors. So something like 1509 went for the first detection of gravitational waves, like went in here. For a little while, it was an in-spiral regime, and then it quickly went to the merging regime, and then it's a ring down. So in stellar mass black holes could go even further. So they would be down here, and they would something like 10 solar masses would be about right there. So if you start, and this was only like a 3629 solar mass. So if you go higher and higher in the masses, it'll go below this inherent noise curve.
Two-part question, but they have nothing. Two parts have nothing to do with each other. You can ignore the second half. So first is, how is the orbital radius related to the event horizon or the other parameters of a black hole? And the second part is, in those animations where you see the black hole against the backdrop of the Milky Way, is the size of the black spot, what's that radius? Is that the same as the event horizon, or is there regions beyond the event horizon, but where I can't see the light kind of directly skimming that tangent line?
I think Leo should talk about that.
Okay, so for the mic, the question was about light orbiting a black hole and what is the dark region that you see in those ray tracings. So the radius of light orbiting the black hole for a non-spinning black hole is 3 times the Schwarzschild radius, and that is in every direction. It's always a circle. And if you have a spinning black hole, then the radii that are possible depend on, there's a certain direction to the spin of the black hole, and then there can be closer orbits that are going in in the opposite direction of the spin, and there are farther orbits that are going in the same direction as the spin. And the entire range between those two is allowed. If you want the formula, it's on the website. It's on that webpage. But they're all outside the event horizon by some certain amount. Now, when you look at the ray tracing, the dark region that you see corresponds to the light ring, in fact. So it corresponds to those photon orbits. Because if you think about the light rays that are coming to your eye, that are coming from behind there, and trace them backwards in time, the ones that would never have made it out would have, if you go backwards in time, they could have just been going in a circle forever around the black hole. And closer than that, it would have had to have come out of the horizon, which is not possible. So the light ring is, in fact, the region that you see as the dark shadow in the ray tracing. So it's not the event horizon. It is, in fact, the light ring.
Oh, sure, yeah.
Would there be a reaction if a really big black hole was to be next to a planet?
Well, it depends how far the planet is from the black hole. As Leo said, if you're very close to the black hole, then the planet will fall into the black hole. If the planet is far away in a stable orbit, it will keep going around the black hole. The very big black hole will be the stronger player in this scenario.
Okay, so the question was, can I talk more about radio astronomy techniques? And so obviously that's a very broad question. The field of radio astronomy is gigantic, but I'll say a few things about what I do as a proxy for your question. So I use this instrument called the Very Large Array. The Very Large Array is basically these 27 satellite dishes that are each 25 meters in diameter. And what you do is these 27 satellite dishes together simulate one gigantic dish, right? And these dishes are sitting on these railroad tracks in a Y-shaped formation, and you can move the dishes' positions relative to each other. And the farther away you make the dishes from each other, the better resolution you get. But this comes at a trade-off in sensitivity. So the worse, you can only see brighter things. Some of the fainter things you won't be able to detect. And if you want, you can come talk to me afterwards. I don't think I have enough time in this panel to explain exactly how that works. Mm-hmm. Yeah. So the Y shape actually is not an optimal shape. And this was not known in the 1970s when the VLA was built. If you look at all the new radio interferometers that are being built right now, they look a lot more random. And it's really because if you have a lot more random positioning of the dishes, you get much better snapshot coverage of the sky. If you look at your thing for only 5 minutes or something, then your missing data is not, there isn't really a pattern to the data that you're missing. And again, you can come talk to me afterwards about it. But yes. Mm-hmm. Oh, yeah. Mm-hmm.
I just want to add something cool about radio telescopes. So roughly the idea is that the longer the wavelength of light you have, the bigger the telescope that you need. So optical light has much shorter wavelengths than radio light. So radio telescopes are huge. So the Very Large Array that Dylan was talking about, there are 27 dishes. Each dish, it looks like a satellite dish, but each one is about 10 stories high, and the dish itself is about the size of a baseball diamond. So you can climb around on these things, which I think both of us have before. There's a single dish called the Green Bank Telescope in West Virginia that's 100 meters across, and you can take an elevator up and down. And then there is a dish and the Green Bank Telescope is actually the largest steerable object on land, on the Earth, because it can actually point around. When you get bigger than that, you get a 300-meter dish, which is in Arecibo in Puerto Rico. That was featured in this James Bond movie. He kind of runs around the dish. That is so big that it can't be steered anymore. It's just sitting in the ground. It can be steered through some sort of instrumentation techniques, so you can actually physically move the dish. So these are really impressive feats of engineering. Yeah, in the back.
So this is sort of a process question. If you were to consider all of the drivers of scientific discovery, individual genius, government funding, philanthropic funding, diversity of ideas and perspectives, specific technologies that have accelerated scientific discovery, which ones might you put
That's a tough question. So the question was, under what conditions do we think that scientific discovery can flourish? Is that what drivers, like funding, individual genius?
All the reasons for scientific discovery. Rare geniuses like Einstein and Hawking, or just we need to throw more money at the problem.
Yes.
We need to have more collaborative culture.
Yeah, so I guess for the recording, the question is, what are the drivers that enable discovery? How would you weight various factors such as individual genius, funding, sorry, what were the other things you listed?
I mean, it could be a specific technology.
Yeah, technologies. Yeah, I think do we want to just go down and give some ideas?
I'm the first one to answer. So I would say all of those. I mean, yeah. I mean, it's a better education system, more funding for science, and just diversity and inclusion as well. I mean, there's a lot of kids who grow up in the world without a good education, or very poor communities, and there could be a lot of geniuses out there that just don't get access to education.
Yeah, I think I agree with Ron that you need to create an environment that these geniuses will flourish. And that's creating a society that has interest in science and creating an environment that will keep these people doing science, and also in order to keep those people doing science, you have to pay them, and it's all of them. It's just interests coming together and having a positive impact.
Yeah, so I guess to add on to that, I would say that there's this conception that all physicists and all astronomers are geniuses, and that the only reason why we're here is because we were just born and just came out of the womb and we're like E equals MC squared, right? And that has definitely not been my experience. So you don't need to be a genius to be a scientist, not at all. You just need to work hard, I'd say. And you need to be given the opportunity, and you need to have the resources to be able to, do the thing you love. And I would say that a lot of science these days, you look at, the amazing discoveries that are coming out of LIGO, for example. If you ever look at that paper has like 5,000 authors or something like that, right? And it's all these people were significant. I mean, everybody contributed their own bit. Some people contributed more than others, but you can't build these scaffolds of scientific discovery without having lots of people working together. And it's not saying that any given problem has to have lots of people in order to solve it. There are plenty of small collaborations that are doing great science, but also the more people you have, the more scientists you have, generally the more discoveries you're going to make, I would say.
I don't know. That was pretty comprehensive. I'm not sure what I can really add to that. I guess one thing that came to mind is that I think the nature of the way science is done is to have a very kind of questioning attitude, and for people to feel comfortable challenging ideas and having their own ideas being challenged, for nothing to really be off the table to discuss or propose. And I guess I'm just thinking that you need society to kind of be, to have the right conditions to allow for that.
I think almost everything's been said so far. But we can look at some historical examples to see like what made conditions ripe for science to happen. Nowadays it's pretty obvious that we need governments to fund science. There's big projects that nobody can do individually. But that was true back in the day too. It's not some modern thing. Science has always been funded by, back in the day, there was the Vatican needed astronomers so that they would know, when was Easter really going to come, because the calendar kept changing because they didn't know how to keep track of time properly. So it was the church that was funding science. So science is really like supported by all of community. It's not just like individual people. And then if you go back to when electromagnetism was being worked out. You can see Michael Faraday was not trained as a scientist. Michael Faraday worked as a bookbinder and worked as an apprentice to a scientist, and basically just picked up science by working as an apprentice. He didn't come from privilege like Newton came from privilege, so he had lots of free time and luxury. Like Darwin came from privilege, he had lots of money. So there were people of privilege who obviously had lots of resources to do science. But then Faraday got the opportunity to do science by working as an apprentice, and it was really Faraday's intuition and working with materials in the lab and doing lots of experiments that led to Maxwell being able to formulate the modern theory of electromagnetism. It wouldn't have happened without Faraday. So this is, his history points us to valuing the diversity of backgrounds and not just having people from privileged backgrounds coming to participate in science.
Why do we continue to look for dark matter as opposed when we haven't found looks like dark or would suggest evidence of dark matter actually existing as opposed to some alternative explanation like emergent gravity or entropic gravity? There are kind of new thoughts on a better explanation of what we're looking for? In terms of, like, for example, you could look at the rotation of the galaxy and say that, the speed of the rotation of the galaxy at different lengths would suggest that there's something else there. There's dark matter, but there are also other explanations to describe that we can't necessarily test or have an experiment to test that.
Yeah, okay. So the question was about the different ways that people try to understand the dark matter problem. So it's true that the kind of consensus view in the community is that dark matter is some new particle that we don't understand. This is called weakly interacting massive particle, or WIMP. But other people are working on other proposals, like you mentioned a few of them, entropic gravity, for example. Now, the thing is that it's not just one observation that any of these proposals has to explain. There's really this combination of all of these different observations that point to the same more or less simple model. Well, whether or not it's simple is a different question. But any model has to simultaneously explain galactic rotation curves, lensing measurements of mass versus the amount of baryonic mass that we see with electromagnetic observations. The cosmic microwave background has a certain signature due to the difference between ordinary baryonic mass and dark matter. The clustering of galaxies and galaxy clusters on very large distances has a telltale sign of the amount of dark matter versus ordinary baryonic matter. There's a whole slew of astronomical observations that all fit together, and they all can be explained with this one model. Now, this model is not super explanatory because all it's telling you is there's this stuff that acts like it doesn't have any pressure, but here's how much of it there is per unit cubic centimeter in the universe. So this is not telling us anything about the nature of dark matter. It's just telling us that whatever the explanation is, it has to act like this stuff that doesn't interact very strongly. It has to be pressureless, and here's how much of it there is. Now, the question is, do other things like entropic gravity, for example, give you that same prediction? I don't really know. Other people are working on it. But in the end, if you look at these theories from the point of view of something called effective fields theory, almost anything that you do means that you have to add another additional degree of freedom or multiple degrees of freedom. So all of these things end up looking more complicated than the standard model, either with just one new field that we call the WIMP or the dark matter particle, or a bunch of extra fields. And some people can argue about the semantics of whether or not you say that's matter and that's gravity, but in the end, it's just extra stuff that you add to the model. And I think the distinction between it's in the matter sector or the gravity sector is kind of artificial. We're adding more stuff to the model that goes beyond the model, and we know how it acts. And the WIMP is the simplest way so far that we understand how to explain it. Okay, what does pressureless mean? So when you model the universe on very large distances, there are different types of fluids. I mean, we model essentially almost everything in cosmology as a fluid, even though these things aren't really fluids. But pressureless just means that if you squeeze it, it doesn't squeeze back at you. So if you take just a collection of dust floating around in space and you try to squeeze it together, that doesn't squeeze back at you. If you take a gas that, the gas particles start bumping into each other when they get dense enough, that does squeeze back at you. So that has pressure. Dust does not have pressure. Dark matter seems to interact with itself so weakly that if you squeeze on it, the dark matter particles just go straight through each other, so it doesn't squeeze back at you.
That equation, the time it would take for the 4 million solar mass black hole to dissipate?
This is just for a 1 solar mass. Yeah.
What was the time it would take? And so that's its lifespan, basically.
Yeah. Yeah. This one was 10 to the 70 times the present age of the universe. So 1 followed by 70 zeros times 14 billion years.
Yeah, so earlier I kind of made the mention about how you sort of get frozen on the star to some outside observer. They see you get frozen right there. And because as you get closer and closer, they'll see you as if your time is going slow and slower. So let's say that, they can see your watch on your hand, for example. So as you go further and further into the black hole, closer to the event horizon, the ticks between seconds will go slower and slower and slower to pretty soon, like when they're still looking at you, they're going to see like, oh, his clock stopped ticking. They're like, okay. And you would eventually get frozen onto, your image gets frozen onto the black hole, and then you get what we call infinitely redshifted. The wavelengths of the light get stripped so far apart, where they go past the, the infrared to where you just don't see it anymore. And essentially your image disappears. And what you would see as you fall into the black hole is that you would go and get closer and closer, and then pretty soon you would start to see this this black hole sort of form all around you, and you get to a point where your entire horizon will look dark. It would be like as if you were at the surface of the black hole, but that's not actually true. Actually, you go further and further, and you'll start to look out, and then you'll see everything encapsulate, sort of like around you. You'll start to see a circle of light, and what that is actually is all the light in the universe being gravitationally lensed. So all the light in the universe being warped around, to where it's like you can see the entire universe as this giant circle right there. And eventually your toes will go into the black hole and you would get spaghettified.
There are animations on this guy's website. If you search for Andrew Hamilton, I believe, Colorado, he has simulations on his website. You can see what it looks like.
So the question was, if a star went close to a black hole, like can they exist as a companion, or does the black hole suck it up? Okay, yeah, so that was the question. So Leo touched in his talk earlier about how black holes are not vacuum cleaners. So if the star is far enough away, it can orbit it. They can be companions in a way. And so with something like black holes, when they're really close together, really compact objects like even neutron stars, they start to emit gravitational radiation. So that causes them to inspiral into each other. But if you have a normal star, which is not compact, far enough away from the black hole, they can be companions for a long, long time until the star would eventually, go supernova and explode. But if it was a neutron star and it was too close, what could happen is that you'll get emission of gravitational radiation, and that causes the neutron star to slowly inspiral into the black hole, where a couple things could happen. We're not entirely sure what would happen right here because we don't know how the interior of a neutron star behaves. We don't know what we call the equation of state. Like, are they really stiff stars? Are they kind of soft stars in a way? If they're soft, then the black hole would rip it apart. If not, then it would just kind of like get swallowed in a way. But yeah, stars can exist as companions with black holes, but black holes are not like vacuum cleaners. They don't go around gobbling everything up. But if it's a compact star and it's really close to it, it can eventually inspiral into it.
Yeah, so I just wanted to add to that and say that you know how we were talking about spaghettification earlier, and how the force on one side of your body is different from the force on the other side of your body? That can happen to stars too. So the force on one side of a star could be much less than the force on the other side of a star. And sometimes when the star gets a little bit too close to a black hole, the star can get ripped apart by the black hole. And this is something really cool and something we actually see. It's called the tidal disruption event. And what happens is when the star falls in and gets very close, about half of the star's mass gets ripped off of the star and starts spiraling into the black hole, and the other half of the star's mass gets ejected out into space. And in the meantime, before it gets ripped apart, actually the star, because there are these up and down tidal effects as well, the star sort of gets flattened like a pancake, and then it bounces back from the pressure. And all sorts of amazing, weird things can happen. And tidal disruption events are an area of active research. People are looking for them all the time, and nobody really is able to explain all the things that we actually see so far. Yeah.
I hope you're finding my question, but I think I'll ask you mostly because you seem like you're a GR person. What's up with SYK?
SYK? Yeah. I actually don't know what SYK is.
I don't know what SYK is either.
The SYK model. You're not familiar with that? No. Really?
Is this Kataev's model?
Yes.
Yeah, I don't know anything about it.
Okay, I'll refine my question. I'll ask you that. I'll ask you that question. What is an extremal black hole?
Okay, what is an extremal black hole? I can answer that one. Okay, so in general relativity, I already mentioned that black holes can spin. There's a certain amount of spin, that angular momentum that they're allowed to have. So the Earth is spinning. You could imagine that if you spun the Earth faster and faster, that it would get more and more deformed. It would become more oblate. And eventually, if you spun it fast enough, then the stuff on the equator would kind of get unbound. So with a black hole, something funny happens if you try to spin it faster and faster. It also becomes more oblate. Now, black holes, it turns out, are also have like a maximum speed at which they're allowed to spin. So just like if you tried to spin the Earth too fast, it would break apart. Black holes are not allowed to spin faster than a certain speed. But it's not because they break apart. It's because the laws of general relativity say that if you try to spin it too fast, then the event horizon goes away. There wouldn't be an event horizon there. So the boundary between where you do have an event horizon and you would no longer have an event horizon is called extremal. So the max in the right units, the maximum spin that a black hole can have, the J, is m squared, where m is the mass. In units where the speed of light is 1 and Newton's constant is 1, which, okay, astronomers will hate me for that, but sorry. So there are other ways to make a black hole extremal besides extremal spin. You can also add charge to a black hole to the point where the horizon would go away, and that would also make it extremal. Or you could have any combination of charge and spin. There's an entire family of black holes that are extremal, and they have really interesting properties. So I talked a little bit about Hawking radiation. So the temperature or the wavelength of the radiation that's coming off of a black hole depends on something called the surface gravity of the horizon. And something interesting is that when the extremal black holes all have a 0 temperature for their Hawking radiation. So they stop radiating once they get extremal. So these are really cool types of stars. They have the math is really beautiful. There's lots of interesting things about extremal black holes that makes them cool to calculate with, but it's probably not relevant for astrophysics because there's always stuff around and it stops it from being extremal. Okay, so first question was how do you add charge to a black hole? Yeah, this is not really astrophysically relevant because the universe is on the balance about neutral. So if you wanted to, if we had a black hole in the lab, which we don't, I would love it if we did, but if we had a pet black hole, then we could have like an electron beam that we could fire into it to charge it up. So like electron beams like we had in cathode ray tubes before we all switched to LCDs, you could shoot electrons into it. The thing is that if you started to charge up a black hole, it would get more and more charge. That would mean that eventually it would start to repel the electrons that you're trying to shoot into it to add more charge. So out in the real universe, there's plasma floating around all over the place. There's lots of both positive and negative charges floating everywhere. So if you ever get a black hole that somehow managed to eat more electrons than protons, so it was net negative, that would mean that it would end up repelling negative charges that were nearby and attracting positive charges that were nearby. So it would end up becoming neutral in the end. So it's really hard astrophysically to charge up, to electrically charge a black hole. The second part of the question was, is space expanding in any direction? And the answer is no. There's no preferred, as far as we can tell, there's no preferred center to the universe, and there's no preferred direction in space. Every direction looks the same. So it's kind of hard to grapple with expansion if there isn't a center. And the analogy that you usually see is like if you take a balloon, and we were all like little ants that were living on the surface of the balloon, and for some reason we didn't understand that the balloon was three-dimensional. We thought that it was only two-dimensional. We were just crawling around on it. If somebody was then blowing up the balloon, we would see all of our ant friends getting farther away from us in every direction. So it would seem like we were at the center of our universe and that all of the different directions were going away from us. But in fact, no point on the surface of the balloon is the center. The middle of the balloon is the center, but that's just because the balloon is a two-dimensional thing that's inside three dimensions. But in fact, you can have, mathematically, you can have expansion in all directions without living inside a bigger space. Yeah, first galaxies, every direction.
Okay, so someone please correct me if I get my cosmology wrong, but yes, there is a place, there is a distance at which the recession velocity of the universe is greater than the speed of light. And no, I don't think that's the size of our observable universe. Yeah, so
I would say at the very early stages of the universe, when we have this very rapid expansion, then it expanded faster than the speed of light. So the universe...
This is another myth that I want to bust. Expansion in cosmology is not measured in the units of speed. So expansion is measured in units of like percent increase per unit time. So it's not a velocity. So you can't say that like the universe was expanding at a certain speed, but if you take something that's a certain distance away, then you can say that in 1 second it'll be that distance times 1.006 whatever units away. So if you take this parameter called the Hubble parameter and you multiply it by the distance, then you get a speed. So if you say how far away does something have to be to look like it's moving away from us at the speed of light, then that thing is called the cosmological horizon. There's a name for this distance away from us. But the thing is that this is really just an apparent velocity. So you're not really allowed in a curved spacetime. You're not allowed to ask, how quickly is this point moving away from this other point? That's a different type of question than in ordinary velocities that we learn in mechanics class, where we can just add velocities. So we're allowed to add velocities that live in the same place in spacetime, but we're not allowed to add or subtract velocities of between here and 3 billion light years in that direction. They're just like it's not an operation that makes any sense. So you can observe something and it can look like it's going away from you at a certain speed, but you're not actually breaking any of the rules of how fast are things moving, because it's not a thing that's moving through space-time. It's space itself that's expanding at a certain speed. There was a second part to your question, but I don't remember what it was.
So you're talking about star formation and understanding and that being a prerequisite for a black hole. But then there are these supermassive black holes that are 21 billion solar masses. And so how did they get there? So is that in any way an indication that we're wrong about the age of our universe?
Yeah, so the question is, how did we get these 21 billion solar mass black holes? And as Leo was talking about during his talk, you have to, we think the largest black holes come from these galaxy mergers, right? And so you get 2 large black holes, and then they merge, and then they become an even larger black hole. But eventually you have to start growing these seed black holes, or you have to start growing these black holes from seeds. Right? And the problem is that you have to start out with some relatively large seed in order to be able to get the masses that we observe today. And that is an open question as to where these seeds come from. Some people think that it may come from this direct collapse of giant hot gas clouds. And so you may be able to get your 1,000 to 10,000 solar mass black hole to begin with, just from one fast collapse. But nobody really knows. Mm-hmm. Yeah. Mm-hmm.
When you did that quiz and you asked what would happen if the sun turned into a black hole and the answer was nothing, is it nothing just pertaining to like nothing's going to get sucked in or thrown out? Because if the sun was to turn into a black hole, everything would die, right?
Yeah, that's right. Yes. So, right. So the Earth could keep going around, but it would get really cold, and all of our plants would stop photosynthesizing, and then we wouldn't have any food to eat, and we would slowly starve. So that would be very sad. So, right. So it's not nothing, but the Earth would keep going around. Yeah. Our orbit would not change.
Nothing gravitational.
Right. Yeah. There were 2 things that I showed. The first one was like star versus black hole, both in GR, and there the orbits are the same. But one was GR versus Newton's theory of gravity, and there was a difference. So, but we have GR, so we're going to have the same speed whether it's a star or a black hole.
Okay, so with something like the star, if you want to shrink it down to a black hole, something like the sun, shrink it down to a black hole, it has to be really, really small, right? And most of the relativistic effects, all that stuff that happens, like, gravitational wave emission and all these things have to happen really close to the black hole. So in order to observe all those relativistic effects with the sun, without it being a black hole, you have to be inside the sun to observe that stuff. So right now, there's like nothing orbiting the sun that's like, inside of it, I guess. I don't know. But whatever's orbiting inside of it is going to be a part of the black hole anyways. So I mean, like, you could see that effects once it turns to a black hole, and if you decide to travel really close to it, then yeah, you'll observe all those relativistic effects. Yeah.
So I just wanted to add that there's a mathematical theorem in general relativity that all spherically symmetric things outside have the same geometry. This is called Birkhoff's theorem. So if you say a star that's spherically symmetric, or a planet that's spherically symmetric, or a black hole that's spherically symmetric, of the same mass, except that we can't make planets and stars that are the same mass, but whatever. They're all going to have the same geometry. But the difference between a black hole and a bunch of rocks or a bunch of gas that's all collected in the same place is that the only numbers that go into describing the shape of space-time around a black hole are just its mass and its spin and its charge if it has any, but usually just mass and spin. Whereas there's nothing keeping the Earth from having big mountains and deep oceans and stuff like that. And all of that stuff changes the gravitational field outside in slight different ways. So that means that satellites that are going around the Earth are moving in a slightly different way than if you replaced the Earth with a black hole of the same mass, just because the Earth is not really spherically symmetric. It's close to spherically symmetric, but if you look at the fine details, then there are tiny differences between how things move around a perfectly spherically symmetric body versus a body that's not spherically symmetric. So those are called higher multipole moments, and for ordinary things like planets and stars, they're allowed to have different multipole moments, but a black hole's multipole moments are totally fixed by just its mass and how quickly it's rotating.
So I think what Leo was just saying is that it's the mass, but then also the shape.
So it doesn't matter if it has rock or...
So the material doesn't matter, but the shape of it matters, and the shape is usually related to the material. I guess that's how it comes into it.
So this is probably a whole lecture, but how do you look at a black hole and decide what its spin is or if it's not spinning?
So I'll start with something, and that is that recently, or maybe actually Ron should talk about the LIGO, the way that from LIGO you can measure the spins.
Measure through accretion as well. You can answer that part.
I mean, do you measure, it's spinning by what stuff around it is doing?
Yeah, so you just measure the environment around there. So for example, the accretion onto a black hole, and the jets that are being emitted, what the potential explanation of that could be. And you can actually get really good measurements on some of the spins of some of these black holes that are not in binaries per se,
Are you really sure the black hole is spinning, or is it just the stuff around the black hole?
I think it mostly has to deal with, the jet and stuff like that. I mean, there are possible explanations that they measure. So some of these black holes that they measure the spin electromagnetically, they're very high spins. But yeah, there's potential that all the physics that are known in that process, have all these errors that maybe they're not spinning that quickly. I think, so they're not going at m squared, for example. They're like at 0.9 m squared or something, because the angular momentum is like, I think the maximal spin is m squared. I would say there is probably no non-spinning black hole. Mostly because is that when you get a collapse of a star, it'll retain the angular momentum of the star. So it'll be spinning to some degree. But also another way we can measure spin is through gravitational waves, which our signals right now, well, there's too much noise in the background right now to really say whether or not these black holes are spinning. So what happens when you get two black holes that spin